Hey folks, MASH is back, and today we're going to be doing the 2022 High Chemistry Paper 2. So yeah, this is going to be full walkthrough of the entire paper, and we'll get straight into it. So, question 1. Elements and compounds can exist as diatomic molecules. The set of elements that exist as diatomic molecules are shown in the periodic table below. Explain why diatomic elements form non-polar molecules. And that's because the atoms have the same electronegativity, and yeah, that's it. And the reason is okay, I can't actually spell electronegativity apparently, but reason for this is if the electronegativity is a measure of how strongly atoms pull on electrons. So if you're pulling at the same strength, then the electrons are going to be like in the same location, right? It's going to be perfectly in between the atoms. So that means that there's not going to be one atom that has more electrons and has more charge than the other. So there's no polar. So it's going to be not polar. So yeah. Nitrogen, oxygen, and fluorine are found on the second period of periodic table. Explain the decrease in covalent radius going from nitrogen to fluorine. Okay, so why is this? Well, as you go across nitrogen fluorine, notice that the atomic number goes up, and atomic number means number of protons in the atomic nuclei, which that means that you have more. The nuclear charge is stronger because it's got more protons, so it pulls on the electrons, with more strength, pulling them closer to the nucleus. So that's what we're going to say. We're going to say an increased number of protons. Plus increased nuclear charge. Which pulls on the electrons with more force, pulling them closer to the nucleus. I can never actually spell nucleus, but there we go. First ionization energies decrease going down a group. State what is meant by the term first ionization energy. So basically what the clue for this one is actually if you go to your fancy density data booklet, scroll down a bit, you'll get to the this table here. And this will talk about ionization electronegativity, and it defines electronegativity as the first ionization energy, as this. So it looks like you're removing 1 mole of electrons from gaseous atoms. So you can't just, unfortunately, I don't think you can just state this formula. You're going to have to put it into words. So we're going to go and say the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. So yeah, it's the important stuff there is 1 mole of electrons, 1 mole of gaseous atoms. If I knew how to spell it. There we go, that's roughly it. Explain why the first ionization energy of the group 7 elements decreases going down the group. Okay, well, let's go look at the periodic table again. I know there's one in there's a diagram, but it's good to happen to get used to just looking at your data booklet. So why do fluorine, chlorine, if you go down group 7, why does the first ionization decrease? Well, that's because, look at it, we've got extra electron shells getting put in. And if you've got extra electron shells getting put into your atoms, that means that the outer electron shells will be more shielded by the inner electron shells, so thus require less energy to remove. So that's just what we're going to say. You say more occupied electron shells. So outer shells are better shielded by inner electron shells. So the outermost probably. inner electron shells from the force exerted by the nucleus. Hydrogen halides are diatomic molecules formed between the hydrogen and the elements chlorine, and bromine and iodine. The boiling points of the hydrogen halides are shown in the graph below. Hydrogen fluoride HF has the highest boiling point of the hydrogen halides. State the name of the strongest type of intermolecular force found between hydrogen fluoride molecules and explain how this type of intermolecular force arises. So, well, remember, there's the strongest type of intermolecular force, which is why a boiling point is so high for hydrogen fluoride, is hydrogen bonding, because it only occurs when you have hydrogen bonded to fluorine, oxygen, or nitrogen. So, well, first, we can already get 1 mark by stating hydrogen bonding, and then we just need to go and put a explanation. It arises when hydrogen is bonded to fluorine, oxygen, or nitrogen, and it rises between, that probably makes sense, between molecules that have hydrogen bonded to fluorine, oxygen, or nitrogen. And I believe that's all you need to do. Looking at this correctly. So, and yeah, it's good 2 marks. Right. Yeah, I guess only other thing we could add if we just explain why it's only these elements, as they have high electronegativities. That would just probably make it a slightly better answer, just in case. But there we go. Yeah, so that should probably do it. And we'll move on to C2. The table shows the boiling points of hydrogen chloride, hydrogen bromide, and hydrogen iodide. Explain fully why the boiling point increases from hydrogen chloride to hydrogen iodide. Okay, so, right, so first thing I'm going to say is when moving from hydrogen chloride to hydrogen iodide, total number of electrons increases. A total number of electrons in the molecule, say, actually. Increases, and then this increases the strength of the LDF, London dispersion forces. That's not how you spell London. LDF mean that the LDF between the molecules requires more energy to break, therefore higher boiling points. You never know how to spell boiling, do I? There we go. Move on to question 2. Fireworks contain a range of chemicals including a fuel, oxidation agents, and metal salts. One oxidation agent used in fireworks is potassium perchlorate. This reacts with aluminium metal and produces a bright flash. The equation for this reaction is potassium chloride plus aluminum is potassium chlorate and aluminum oxide. Balance this equation. So let's zoom in here and see what's balanced. So already I see, okay, well, I've got 2 aluminium on this side. I've only got 1 here, so I'm going to add 2 there. But otherwise, we also have 4 oxygens on this side, but we only have 3 on this side. So actually, I think I'm going to have to go and fiddle around with this a bit. So we want a number that both 4 and 3 can go to, so we can keep this in whole numbers. So how about if we times this by 4, we'll have 12 oxygens on this side. If we times this one by 3, we'll also have 12 oxygen on this side. That sounds good. Okay, so that means we actually have 8 aluminium. So we're going to have to go and write 8 aluminium there. And then we now have 3 catapotassiums and 3 chlorines. So that means we're going to have a 3 there. And we'll just do one final check to make sure we've got it fine. We've got 8 aluminium to this side. And we've got 12 oxygens, both on both sides. And we've got 3 of that. There we go. And the equation is balanced. Fireworks were traditionally made using compounds containing the chlorate ion, which is ClO3- as an oxidation agent. Oxidizing agent, sorry. Chlorine releases chlorate ions release oxygen when they decompose. Potassium chlorate reacts as shown. Calculate the volume of oxygen produced in liters when 4.6 grams of potassium chlorate decomposes. Alrighty. So effectively, what it's saying is we've got 4.6 grams of this stuff, and we want to just see how much oxygen we get produced. So let's go and start by saying how much moles of potassium chlorate we have. So we'll use the molar mass formula, or whatever it's called. So it's basically just N equals M over Fm. So we know the mass is 4.6, and the general formula mass is 122.6. So then we can pull out our calculator. 4.6 divided by 122.6 will get us this number, 0.0375. ... Just keep this number in your calculator. You don't really need to write it down because it just makes it far easier. And then what we're going to do is we want the volume of oxygen. So we know that 2 moles will make you 3 moles of oxygen, which means we need to basically divide this by 2, then times by 3, because it's a 2 to 3 ratio. So I'm going to divide by 2. And that'll give us 0.0188. And then I'm going to go and times by 3. And that'll give me 0.0563. So yeah, this is the amount of moles of oxygen we now have. So since we know the amount of moles, it does say the volume of 1 mole of oxygen is going to be 24 liters. So we can actually go and pull up our molar formula, which I believe is V over mV. So we know how many moles there are, 0.0563-ish. And then we don't know the volume, but we do know the molar volume is 24 liters. So we're going to times 24 by that and see what we get. And then with 1.351 liters. And there we go. The decomposition of potassium chlorate can be speeded up by the addition of a catalyst. State the effect of adding a catalyst on the enthalpy change for this reaction. Okay, so how we're going to figure out this? Well, if you're stuck on stuff like enthalpy change reaction, what I'll do is I'll actually draw a graph, and we just go and make something up. It doesn't specify. This is a fireworks. So it's probably actually a exothermic reaction, but it doesn't really matter. We'll just draw a simple reaction graph any other way. But remember, adding a catalyst, right? What it actually does is it provides an alternative reaction pathway. That means that you need to put less energy in. It reduces the activation energy, essentially. But notice this shoddy graph I've drawn here. They go to the same point. It doesn't change the enthalpy on the reaction. You know, if I make a reaction, if I burn something and I add a catalyst, it doesn't mean I'm going to get more energy out of it, or it just means it happens faster. So that means the answer for this is going to be no effect. A firework containing 5.5 grams of potassium perchlorate releases 103 kilojoules of energy. Calculate the energy in kilojoules released per mole of potassium perchlorate. Okay, so what we're going to do here is go and calculate the number of moles in 5.5 grams, and then, well, it'll be the number of moles, and then we can use that to figure out how much 1 mole would produce. So we're going to go say N equals 5.5 over 138.6. What we get there, 5.5 divided by 138.6. When I get this number, this is how many moles there are, so it's roughly 0.04, but we'll put dot 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 to say that. Yeah, always remember to store your numbers in your calculator and round up at the end. Okay, so that means what we can do is we can divide this by this, and we'll get our the amount of moles for 1 mole of potassium, the amount of energy released by 1 mole of potassium perchlorate. So that means I'll go and copy this. We'll go. You can just use like the answer button on your calculator, but Windows Calculator actually is terrible, so I have to do this. So this will mean that 1 mole. Let's see if we'll just put divide 103 over here just to see what's going on, and that will give you 2,595.6 kilojoules. And they really want kilojoules to be like the J to be obviously bigger than the K because they're the absolute pedants, but there you go. Explain fully why increasing the temperature increases the rate of a chemical reaction. Okay, so increasing in temperature increases the increases the average kinetic energy of the particles in the system. I'll extend this out so you guys can see it, meaning more particles have at least as much energy that's the activation energy for the reaction. So they can react, and since the particle is moving faster, collisions are more likely. So more successful. So successful is when the particles actually combine. Collisions occur. Boom. And I guess they also want to talk about. You could also mention stuff about activation, the activated complex, but it's probably long enough as is. The different flame colours produced by metal salts are caused by different wavelengths of light being emitted. The flame colours associated with different wavelengths are given in the data booklet. The following profile shows the colours emitted by one particular firework. Each peak represents a different colour of light. Peak A has a wavelength of 620 nanometers, corresponding to red light, suggests the metal responsible for peak B on the spectrum. Okay, so peak A is 120 nanometers, so that means peak B would probably be, we can use that to just figure out what it would be, and it looks like it would be 590 nanometers. So yeah, let's go and go to our data booklet and see if we can find anything useful, because there should be, if I remember correctly, there'll be a nice table when they'll tell you about the different colors that infrared correlation tape. No, that's not it. So spectral lines and flame colors. I've basically never needed to pull this out, but it is a first time for everything. But as you can see here, if we're looking around, it's going to be what's a metal that would give you 590. It looks like it'll be sodium. It's 589. That's practically 590, all things considered. And yeah, well, helium is close as well, but it's not a metal, so I don't know what to leave. So that means metal would be sodium. Oh, and we've got our first using knowledge of chemistry question. Atoms of different elements have different attractions for bonding electrons. Electronegativity is a measure of the attraction an atom involved in the bond has for the electrons in the bond. Using a knowledge of chemistry, discuss the importance of electronegativity in bonding structure and properties of compounds. Okay, so before you do something, go on a list of what you're going to talk about. I think I'm going to talk about the covalent to ionic spectrum, because basically the more different an electronegativity is between atoms in a bond, that means that it's more likely to be a pure covalent or a polar covalent or ionic, depending on the difference in electronegativity. But you can also say stuff about PDP interactions / hydrogen bonding versus LDFs. You can say, okay, well, if you've got a bigger difference in electronegativity, you can have stronger intermolecular forces. And you can also talk about oxidation agents as oxidation agents as higher electronegativity means they want to get more electrons, so they're good at oxidation agents. So let's go through these one by one and just start yapping on. So the difference in electronegativity between two atoms, in a chemical bond determine the type of bond. If the difference is 0 or very small, the bond is non-polar covalent. So the atoms will share the electrons equally between them. If the difference is larger, then it will be a polar covalent, meaning that one atom has more of the electrons in it, has electrons closer to it, so is negatively charged. Sorry. Right, we'll get back to it. So are negatively charged. Probably partially, because they're not going to be partially charged, while the other atom will be partially positively charged. If the difference is very large, then an ionic bond is formed, where the atom with the higher electronegativity rips the atom with the lower electronegativity electrons straight off and adds it to their outer shell. Ionizing themselves and their atom and the other atom. Okay, so I think that's a lot we've already talked about. Let's see if we can move on to PDB reactions / hydrogen bonding with LEF. Non-polar covalent bonds. Covalent bonded molecule. Say molecules featuring non-polar covalent bonds or ionic bonds can form PD interactions, and let's put in brackets around PD permanent dipole interactions with other molecules, or if the molecule has hydrogen bonded to either nitrogen, oxygen, or fluorine. Hydrogen bonding. PD or hydrogen bonding are much stronger than LDF and dispersion forces. Oh, sorry. And thus, compounds with them present have higher melting and boiling points as more energy is required to break the van der Waals forces, just to be really fancy, between the molecules. Yeah, probably a bit more we can talk about there, but let's go and move on to, I don't know, oxidation agents. Elements with higher electronegativities are more likely to be good oxidation agents, as a higher electronegativity means, which one thing I probably actually forgot is that if you're doing something specific like in electronegativity, what you want to do is you really want to give a definition of electricity. So actually, let's go at this top here. I'm just going to say electronegativity is the tendency of an atom to attract a bonding pair of electrons. And remember, we also got, I do tend to go off in a bit of tangents with these questions. I don't go and I always kind of forget to follow them to the letter, but you also want to talk about bonding structure. Indeed, you have to say bonding structure and properties of compounds. We've done a lot of bonding, not so much structural properties of compounds, so that's probably what we're going to talk about next. But we talk about oxidation agents now. electronegativity means that the atom is more likely to applies a greater force on other electrons, so can remove electron, so it's more likely to move. From other atoms, oxidizing them. Yeah, we'll leave it at yeah, we do talk about reducing agents, atoms with very low electronegativities are more likely to be reducing agents, as they do not apply a great force on their outer electrons, so other atoms can remove them easily, reducing them. Right, so let's see if there's anything else we can talk about. So we've already sort of talked about the higher melting boiling points with dipolar molecules. Structure. Maybe we could talk about discrete covalent. So we've already kind of. I think this is enough text that they'll probably give it to us. Let's face it. It shows a good enough extent at the end, but I'm running out of room, let's face it. So we'll leave it at that so far. But remember, with these, as you should be doing them at the end of a paper, just write as much as you possibly can. Just blabber on about anything until time goes up, I guess. But I mean, I did say that, but also maybe to go back over and check your answers. So maybe a good balance would be write a page or like a couple pages of your answer, and then go back and go and check over. Just, kind of do what it did. You want to, every exam is all about balance. You don't want to focus hard on one particular thing. We'll move on to question 4. Coconut oil contains a mixture of compounds. Propyl octanoate is a compound found in coconut oil. Name the functional group in propyl octanoate. Okay, well, it's pretty clear to see here is it is a ester. Right, it's got the ester link here, so that's exactly what we're going to just write. Don't be fooled and say it's a carbonyl group, because it's not. So, because it's got this extra oxygen attached to it. So we're just going to say it's an ester link. Draw a structural formula for the carboxylic acid formed by hydrolysis of propyl octanoate. And two ways you can do this. You can have a look at the diagram and use the name, but basically what we're going to do is we're going to find the carboxylic acid is the side with the double bonded oxygen, and as you can clearly see here, it's going to be this one here, and we can check using the name because the carboxylic acid is going to be the second one, the O8, and that's 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. Okay, so that means we got to write octanoate acid. So let's go and get writing. So we see C, 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 C. Now, because it's a carboxylic acid, we've got to put our carboxylic acid functional group, a carboxyl functional group, which would be this. And then we just need to populate the rest with hydrogens. I've heard they will actually accept one omitted hydrogen, but it's not only if the bond is pointing at an empty space. But that seems like such a daft thing to do. Like you notice that pretty quickly. So yeah, just put all the hydrogens you can, because it guarantee you get that mark. There we go. We're done and dusted. An isomer of propyl-octanate with the same functional group was hydrolyzed. One of the products of this hydrolysis was butanoic acid, suggested with the name of the other product. Okay, remember, propyl means 3 and octanate means 8, so total 11 carbon atoms. Which means if butanoic, remember, means 4, so we want them. How many carbon atoms do we have remaining? Well, we will have 7. And it's butanoic acid, which means the other product was going to have to be an alcohol. So that means we're going to say hept, because it's heptan, because it's a alcohol, heptanol, and because it's an alcohol. So yeah, heptan, and hept because it's 7, ol because it's an alcohol. Oh, do you see what I did there? Wrong there? Yeah, that's right. With large carbon atoms, alcohol atoms like this, you're going to have to specify where you put your OH group. So you're going to have to make sure you put that one in there. You can't just say heptanol. Sorry, folks, my mistake. Right, I'll move on to 4b. Chromatography can be used to separate the fats and oils in coconut oil. The results of chromatography experiment is shown. We've got this rather unpleasant looking graph here. Using the graph and the information in the table, predict the number of carbons in glycerol or trilaurate. So don't worry, they're actually quite lenient in this one. They accept a pretty wide range because this one is actually fairly difficult. But the way I would go about it is we know the answers for. I'm going to highlight the compounds we have in the table. So you have tricapillate, we have the other one, caprate, they don't tell me how to pronounce these, and trilinoate at the very top. The way I would do it is I'm going to have a look at these, look at the difference in the carbon atoms, compare them to the difference in retention times, and then hopefully we can sort of use it to estimate what trilaurate is going to be. So I'm going to use these two here because I think they give a semi-accurate answer. Yeah, this one's a bit of a nonsense to be honest. But the difference between the retention time is 1.5, and the difference between the amount of carbons I have is 6. Okay, so that means that if we pull up my calculator, 6 divided by 1.5, that means for every 1 minute of increase in retention time, you get 4 extra carbons. So we can use that because we know the difference between glycerol trilaurate and glycerol tricaprate, and that is 1.4. Going to times 1.4 by thing, we're going to get plus 6 rounding up. So that means we add 6 carbon atoms to 33. We're going to get 39. So I'm going to say 39 carbon atoms. And according to the marking scheme, you can inclusively you can do 35 or 45. So there's actually a couple of different methods you can use. I've done some calculations that's like some of them are like low 30s, like exactly 35, and some of them are more like 42. So there's a couple of different ways you can do it, depending on which difference in absorption time you use. But I'm going to put 39 carbons. Right, I will move into 4b2. Identify the compound listed in the table with them, which is the most unsaturated. So what I'm going to work this out is I'm actually going to use these numbers here to figure out the average number of hydrogen atoms per carbon atom. So we have 27 carbon atoms and 50 hydrogens, so I'm going to divide by 27. So each carbon atom here has roughly 2, but I'll say 1.85 average hydrogen atoms. And the same here, we're going to have 33 divided by 62. 62 divided by 33. That means, yeah, we've got a certainly similar number there. Each carbon atom is 1.89 hydrogen atoms, and then for the bottom one, 98 divided by 57. Each carbon atom has roughly an average of 7.2. As you can clearly see here, the one with the lowest number would have the highest degree of unsaturation, as that means there's less hydrogen atoms, so there's more carbon-to-carbon double bonds, so it's more unsaturated. So that means we can go and write down our answer, which is glycerol tri something or other. I do not want to open the developer tools, thank you very much. this question is ridiculously difficult for no reason at all, but here we are. Edible coconut oil, such as coconut oil, can be used to make emulsifiers. Say how emulsifiers are made from edible oils, and that is by reacting them with glycerol. Right, I'll move on to 2. Explain fully how emulsifiers prevent non-polar and polar liquids from separating into layers. And that's because if you think about an emulsifier, it's going to have an ionic component and it's going to have a non-polar tail. And that means that the ionic one will dissolve in the polar liquid, because polar liquids dissolve, polar solvents dissolve polar solutes, and non-polar solvents dissolve non-polar solutes. So the polar head will dissolve inside the polar liquid, and the non-polar tail will dissolve inside the non-polar liquid and will act as a barrier, preventing them from separating into layers. And that's exactly what I write. I probably should have wrote them while I was speaking rather than just blabbering on. Have a polar head that dissolves in polar liquids and a non-polar tail that dissolves in non-polar liquids. This prevents the polar liquids and non-polar liquids from separating into layers, so the emulsion is stabilized. There we go. Editing, we'll have to cut that awkward silence out as well. Sugar, okay. Right, and we'll move on to 5. Fusel oil is formed as a byproduct using the production of bioethanol for fuel. It is a mixture of several alcohols. The short and structural formula of one of the alcohols contained in fusel oil is shown. State the name of this alcohol. So this should be nice and simple. So you can see already it's going to be a branch chain. So we're going to ignore this bracket for now, but I'm just going to count up how many carbon atoms there are. So we got 1, 2, ignore this, 3, 4. So that means it's going to have a base of butanol, and we see it's on our terminal carbon there, and we're going to start counting from this side. So this will be 1, this will be 2, this will be 3, this will be 4, because we want the functional group to have as low as possible. So we're going to have butan 1-ol, and then this means that this carbon here was going to have a methanol group, and this is going to be carbon free, so it's going to be free methyl butan 1-ol. Propane, oh, it's going to up and disappear. That's really useful, actually. I like that feature. There we go. Propane 1-ol is also found in fusel oil. Propane 1-ol is reacted with an oxidization to produce propanal. Can you complete the iron electron equation for this oxidation reaction? So first things first, I'm going to make sure that a main element is balanced. So C3, yep. Is oxygen's balanced? Oxygen is balanced, but hydrogens are not balanced, unfortunately. So I'm going to have to add hydrogens to to this side, because we've got 8 on this side and we only have 6 on this side. So it's going to be plus 2H, and the hydrogen ions, remember? So we plus 2H plus, or protons, I suppose. And then we just need to balance charges. This side is completely neutral, this side is 2 plus, so that means you have to add 2 electrons on this side to balance it out. Acidified potassium dichromate can be used as the oxidation agent and react as shown below. Suggest why the potassium dichromate must be acidified. Well, looking at this equation, right, you can see that we need hydrogen ions for this reaction to occur. So if it was like an alkali, a base, then you have more hydroxyl ions, which is not what we want. We need hydrogen ions. So there we go. Because the reaction requires hydrogen ions that are provided by the acidified potassium dichromate. State of color change that we observe when propane 1O reacts with acidified potassium dichromate. So remember, when you have an oxidizable, when you convert your chromate into chromium, you're going to go from green to, you go from, this is going to be orange, and this the normal chromate ion is going to be green, so it'd be orange to green. And it should be in a data booklet somewhere, but I can't be bothered to look it up, so just remember it. Remember, so you got your normal, your Cr2O7 minus 2 would be orange, and your Cr3 plus would be green. The equation for the reduction of another oxidation agent that can be used to oxidize propane 1O is shown below. We've got silver, so state the reagent that provides this oxidation agent. And again, this is just more memorization, but it will be Toland's reagent that that has contained silver. And so you'd see that it should actually be silvery coloured. But anyway. Statewide 2-methylbutan-2O cannot be oxidized using these oxidizing agents. Well, that's because if you look at this closely, right, we've got a methanol. I'm going to draw out a small structures formula. We have its base of butanol, but the OH group is bonded onto this carbon here, and this 2-methyl, this methyl group is bonded here, which means we can't actually oxidize this, because doing so would have to break this chain here. To get a double bond for the oxygen, because carbon can only have bond 4 times, so that means that it can't be bonded. So the way we state this in words is because it's a tertiary, it is a tertiary alcohol. In the reaction of butan 1O to butanol, oxidation can be identified by an increase in the oxygen to hydrogen ratio. Complete the table to show the oxygen to hydrogen ratios in butan 1O and butanol. Okay, so we'll just go straight into it. Butan 1O, that is, we've got C, 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 and that means that we're actually going to have, I'm going to draw the full structure formula, but we can also use the general formula, and the general formula for an alcohol is CN H2N plus 1 OH, which means it's H, which means it's technically going to be 10 hydrogen atoms. And we'll just double check using this formula I've just drawn up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's only one oxygen, so that means oxygen to hydrogen ratio we 1 to 10. What about butanol? And now remember, when you oxidize something into an aldehyde, you're going to actually remove 2 hydrogens. But just in case, I'll go. Basically, what's going to happen is you're going to have stuff. You're going to remove those 2 and replace it with a double bond. So that means it would be 1 to 8. Sweet potatoes contain nutrients including starch, vitamin C, and proteins. Catalase is an enzyme contained in sweet potatoes that speeds up the breakdown of hydrogen peroxide. State what is meant by the term enzyme, and it's going to be a biological catalyst. Enzymes are a type of protein. Proteins are formed from smaller molecules called amino acids. The section of a protein is as shown. Circle a peptide link in their above structure, and there's loads of these, but they're all going to look like one of these. So you can choose any one of them. Draw a structural formula for one of the amino acids used to form the section of the protein. So really, what you're going to have to do here is pretend like you're going to hydrolyze one of them to get so you like split it out from the protein. So first draw the kind of top bit with the broken amide bonds. So this is what's going to happen at the top of any amino acids, and then we're just going to select amino acids here. So if you want to be really lazy, you can actually just pick the one on the right and just do a H, and that will actually be correct. But just for the sake of it, because they usually won't give you something that simple, I'll go and pick this middle one. So we're going to have H2, it's CH2, and then we'll have another one, and then we're going to have a sulfur atom, and then we're going to have a methyl group at the end. There we go. State what is meant by essential amino acid. It is a amino acid that cannot be synthesized in the human body, so it must be acquired through our diet. Name the type of reaction that takes place when amino acids join to form proteins. That will be a condensation. As sweet potatoes are cooked, the ability to catalase to break down hydrogen peroxide decreases. To explain fully what happens to the enzyme structure, call this reduction activity. So basically what happens is that enzymes of a certain shape, say this, because they've got amino acids that attract each other using van der Waals forces. So I'm representing here by drawing these blocks. But when you heat them up, what you're going to do is you provide more energy to the system that will break these, which will cause the kind of amino acids to lose their shape. The proteins lose their shape, and if you know anything about proteins, shape is basically the most important thing about them. So you lose their shape, they lose the functionality and don't work. So we just need to put that into text rather than silly diagrams. So we can say increasing temperature breaks van der Waals forces between amino acids on the peptide chain. Meaning that the protein loses its shape and thus denatures, reducing its activity. Hydrogen peroxide is broken down by catalase to produce water and oxygen. An experiment was carried out to determine how much oxygen was produced from the breakdown of hydrogen peroxide by a sample of sweet potato. Draw a diagram showing an assembled apparatus that can be used to react hydrogen peroxide solution with sweet potato and measure the volume of oxygen produced. Your diagram should include labels showing the names, positions of the reactants, and the collected product. Okay. Okay, so this sounds a bit more complicated than it actually is, but what we're going to do is we're going to have a test tube, and we're going to have a solution, and then we're going to have a sample of sweet potato, and then we're going to have a stopper, a tube coming out. And then we're going to have a syringe, gas syringe, so make sure there's no holes in your tubing, and make sure there's a scale on your syringe. And then all we need to do now is start labeling stuff. So I'm going to say this is going to be a solution of catalase, sample of sweet potato. Oh, it's hydrogen peroxide solution. Ignore that. Solution of hydrogen peroxide. Could probably just say hydrogen peroxide at that point, but oh well. And then we just need to label we have to label the gas coming off. So we're going to say we mentioned the volume of oxygen, so we're just going to say oxygen. In fact, I'm going to be really I'm going to also label the inside of the gas cylinder. And there we are. Sweet potatoes are a good source of the antioxidant vitamin C. Antioxidants like vitamin C are added to food. Explain why antioxidants are added to food to prevent the food from oxidizing and becoming rancid. The structure of vitamin C is shown. Explain fully why vitamin C is soluble in water. As you can clearly see here, we've got these OH groups. We've got this double bonded. So yeah, we've got even more OH groups, and that means that this molecule is very polar, so it will be dissolved by water. So you can say vitamin C is polar due to its many hydroxyl bonds, hydroxyl functional groups, and carbonyl functional groups. Glucose. So will be dissolved easily by water, as it is a polar solvent, and polar solvents dissolve polar solutes. Unlike sweet potatoes, while white potatoes do contain the chemical solanine that can be toxic to humans in large doses, a dose of 3 milligrams per kilogram of body weight can cause toxic symptoms. A typical white potato contains 0.2 milligrams per gram of solanine. Calculate the mass of white potato that could produce a toxic dose to an adult weighing 65 kilograms. So, to cause toxic symptoms, we need 3 grams per kilogram of body weight. So we need to have 65 of this adult, and then we have 3 milligrams per body weight of the solanine. So that means 65 times 3. I probably could do this in my head, but I'm not trusting my brain recently. So we're going to do 195. So that'll be 175 milligrams of solanine we need, and a typical white potato can contain 0.2 milligrams per gram of solanine. So then what we're going to do is going to divide this by 0.2, and then give the number of grams. If I divide that by 0.2, I'll give the number of grams of white potato. And there we are. Natural gas is a source of methane. Methane can be used as fuel. Wow, who could have figured that out? In an experiment, methane was burned to raise the temperature of 100 cubic centimeters of water by 27 degrees Celsius. Using the enthalpy of combustion of methane, which is 891 kilojoules per mole, calculate the mass of methane in grams burned in this experiment. Okay, so what we're going to do here is sort of a backwards of calculating the enthalpy of combustion. So enthalpy of combustion, remember, is this is enthalpy change, and it's going to be energy over number of moles. So we don't know energy yet, but we can figure it out because it says it's raising temperature of 100 cubic centimeters of water by 27 degrees Celsius. So remember the heat energy equation. So the mass of 100 cubic centimeters of water is going to be 0.1 because we're doing it in liters times 4.18. Yes, yeah, it'd be 100 grams, 100 cubic centimeters of water, so it'd be 0.1, and then the change in temperature is 27. This means that the energy produced will be 0.1 times 0.148 times 27, which will be 11.29. We'll round it for now. But remember, keep this in your calculator, only round at the end. I'm just rounding down for your convenience. And then it says that the combustion of methane is 189 kilojoules per mole. And then we know that the energy produced by this reaction is 11.29 joules. So now we need to figure out the number of moles. So I'm going to go and divide this by what you can do with these fractions. You can actually swap these two around. So we'd get N equals 11.29 over 891. So I'll divide this by 891. What do we get? We get this number. This is how many moles of methane. Dot dot dot. Yeah, remember, keep the numbers in your calculator as much as possible. Then all we need to do now is use the molar equation here. So methane has a formula mass of, we've got 1 carbon, we've got 4 hydrogens, so this will be 12 plus 4, so 16. So mass would be this times 16, which would be 0.20, and we'll round down to 3, round up to 3 grams. Oh, I didn't speed run that too much. The equation for the combustion of methane is shown. Bond enthalpies can be used to calculate a theoretical enthalpy change for this reaction. Using bond enthalpies from the data booklet, calculate the enthalpy change in kilojoules per mole for the combustion of methane. Okay, so I'm actually going to pull up this. We'll try and do it side by side. So I'm going to scroll to our bond enthalpies here. And now what I'd like to do when I do these questions is make a table. Don't want to make it too big because I want to do some numbers at the bottom. But essentially what we're going to do is say it's going to be bonds broken. And when you break a bond, it takes energy. So it'll be positive because remember, enthalpy change is negative, is giving out energy to the environment, and then plus is requiring energy from the environment. And we're going to have bonds made, which require energy, so which make energy, so are negative. So what bonds are broken? Well, we've got 4 CH bonds. So that means we go over here and we're going to say, okay, well that's like 4 times 412, which we'll just do now, just to save us the time later, is 1,648. And then the other one is broken is 2 of these oxygen bonds, but remember these are oxygen double bonds. Because it's a diatomic element, because they share the same valency. There's 2 of them, so 2 times O, which means 2 times 498. I'll go and do that. 996. And what bonds are made, so what's on the other side. So we have carbon dioxide. Remember, carbon dioxide has the thing, it's double bonded with oxygen, which means it's 2 times C double bond with oxygen, which is 804. And then other one is done is these water molecules. So remember, water, it's like this, so it's just going to be 2. Per water molecule, it's just going to be 2 HO bonds, but since 2 of them is actually 4, and that's 463. Now remember, before you do our calculations, just to double check, this is a combustion reaction and it's with methane, so we should expect to see a negative MPV because that means it's giving energy to its environment. So, oh, I need to go and times these out, don't I? So that would be 1608, and this would be, I'll just use the calculator just in case my brain flips up again. That would be 1852. Right, let's go and add these all together. So on this side we have 1648 plus 996, and then we're going to take away these two. So take away 1608, and then take away that's 18 minus 1852, and that gives us negative 816. Which is the answer. Methane reacts with steam to produce hydrogen. Calculate the atom economy for the formation of hydrogen. Okay, so remember atom economy. I'll just remember this AC because I can't bother to write out the whole thing. Is the mass of desired products over the mass of reactants. And then of course times by 100. So let's go and do that. So mass of desired products, we only want hydrogen, but we do get 3 moles of the stuff, so it is 3 times 2. But then for the mass of reactants, we don't care about carbon monoxide, obviously. So we just have 1 mole of methane, and then just 1 mole of water. So 16 plus 18. So that's 6 over 34, which is 0.16, yada yada, and then times by 100. So we're going to go and multiply that, move the decimal point. So we'll be going up to 17.6%. And there we are. Another naturally occurring gas is nitrogen dioxide. Nitrogen dioxide released in equilibrium with dinitrogen teroxide. Should complete the table to show the conditions that would maximize yields of nitrogen dioxide. So basically what we want to do here is we want to favor the reverse reaction, it looks like. So that means that since this is the forward reaction is a exothermic because it's negative, that means we actually want to increase the temperature, so it will try and do the endothermic reactions are lower. So we want to increase temperature, and then notice they're both gases, right? But we have 2 moles on this side and we have 1 mole on this side. So that means if we want to, when we want to mess around with pressure, we want to actually decrease the pressure, so we'll have it as low. So that means that it wants to make more moles of gas of the thing we want. In United States Space Shuttle, dinitrogen tetroxide to react with methyl hydroxyzine. We've got this horrific looking molecule here. Calculate the enthalpy of this reaction in kilojoules by using the data shown below. Oh boy, now we're talking. This is probably the worst one of these questions I've seen in ages. It's rare to actually get 4 of them, let alone 5 of a state change. But don't worry, it's not going to be it won't be that difficult, I promise you. So first things first, like always, what we're going to do is we're going to go through here and we're going to see if all the reactants are on the correct side. So for this one, this chemical here, I think, it's a methyl hydroxyzine, I think. I'm going to move this onto the other side. So that means we need to flip this. But also notice that in our thing here, that means it's also 4, so we also need to times it by 4. But we'll continue going down. And then we also need to flip this equation here because it reacts with nitrogen dinitrogen tetroxide. And we need 5 of them. Then carbon dioxide is on the correct side, but we do need to times this by 4. So that means we can have 4 carbon dioxides. And then we have, well, this is actually a diabolical wee one, isn't it? So so this hydrogen is in the correct place. This water is in the correct place, because it's going to be, we need water on this side of the graph here. So I think for these ones they should be okay. Right, well, should we just get stuck here, and if I fail miserably then you can yell about me in the comments below. So yeah, what I'm going to do is to start writing these equations out. So I need to flip these two. So we're going to have C3 NH NH2. I won't bother writing state symbols because the only state symbol we need to worry about with water. So it'll be CS, C plus 3H2N, but I just realised I need to times this whole thing by 4, so that should be 12 H2N, 4 here, 4 here, and then plus 4 nitrogen, and the same thing down here. So we're going to have 5 nitrogen dinitrogen tetroxides, and then we have got 5 nitrogens, and then we're going to have 10 oxygen. Right, so let's see if we can start cancelling some of these out. Right, so first off, we do have, that is good. That is also good. They're both on the same side that we want. And then we have, but we also want to get rid of 4C. But luckily, if I'm going to write in the symbols here, for the third equation, we have 4C on this side and 4D's on that side, so we can actually cross them out. The next up, we want to get rid of some hydrogen. Oh, sorry, I mean, yeah, we do need to get rid of some hydrogen. Sorry, I'm losing the will to live here today. Oh dear. Okay, well, while I figure that out, I'm going to remember that we can combine these two hydrogens to get 9 hydrogen. Oh yeah, that's what I need to do. Okay, that's a bit of an idiot moment on my part. We need to have we need to multiply these two equations by 12 down here, so we're gonna have 12. Yeah, sorry about that. I'm not infallible. I'm very fallible, in fact. So we're gonna have 6 oxygens here instead, and then now produce 12 hydrogen water. Then we can produce 12 water in forms of gas. Yeah, this is nonsense in and of itself. So that means we can cancel those two out, and then we have 6 hydrogens here, and then 10 on this side, so we can actually both cancel those out. And then we just need to worry about carbon dioxide. That is what we want. 12 water, that's what I want. These two water liquids, they also cancel each other out, and I believe that should be most of it cancelled. Yeah, because we times this by 5. Yes, we've got everything cancelled out. I know this is very confusing, but essentially what we can do now is go and work out all the enthalpy changes. So yeah, we're just going to add them all up. This is going to be insane. I'll be impressed if I actually get the right answer first time here. So yeah, don't worry about these ones can be quite tricky. Don't worry. I think don't worry. I mean, you probably should be worrying about them, but we've reversed the sign on this one, so this is actually negative 216. And then for this one, we're going to reverse the sign and times by 5, which is 100. And then this one, we're just going to times by 4. Which is negative 1,706. And then we need to times these two both by 12. Oh, it's going to be a long day, ain't it? And that's going to be negative 3,432. And then we also need to times this one by 12. So that'll be 12 times 41, which is 492. Right. So now we just need to add up all these bloody numbers. So 216 minus 216 plus 100 minus 1,576 minus 3,432 plus 492. Oh, that's actually unexpected. I actually got the correct answer first time. There we go. Oh, and it's in it's in kilojoules, not kilojoules per mole, so might want to get rid of that. There we are. Oh, that was horrific. I'm really sorry, folks, but yeah, basically what I do is you want to get all these and make sure they're all cancelled, and then eventually you'll get the correct answer. But yeah, that was really difficult. They shouldn't give you this something this difficult. But anyway, draw the full structural formula for methyl hydrazine. Okay, so it looks like we have a methyl group. That's a really badly placed bond line, but here we are. With a methyl group, then it seems to go to a nitrogen, which is bonded to a hydrogen. This is then bonded to another nitrogen, which is bonded to two hydrogens. So remember, nitrogen only has a valency of 3, so it can only have 3 bonds. But carbon has 4, so just when you're doing this, make sure write that correctly. But yep, that is the correct structural formula. Fizzy drinks are made by adding carbon dioxide gas, preservative and colouring, flavouring to water. Carbon dioxide for fizzy drinks can be produced by using the water gas shift reaction. A catalyst for this reaction is copper 2 oxide. Clear the table by circling one option on each line to show the effect of copper 2 oxide on this reaction. Okay, so it's a catalyst, so that means you're going to increase the rate of forward reaction, obviously, but you're also going to increase the rate of the inverse reaction, which means you're not going to have any effect on the position of the equilibrium because you're tugging in both directions, so it doesn't change. So yeah, catalysts just speed stuff up. They don't change the position of the equilibrium. The water gas shift is exothermic. Draw a line on the axis below to show how the yield carbon dioxide would vary with increasing temperature. So remember, this is yield, not speed, which means that as you increase temperature, so say we're here, if we look at this, remember it's a it's an exothermic reaction, which means that if you increase temperature, it's going to reduce yield. So we're going to have a graph that looks kind of like this, but maybe we could jazz it up a bit. We'll say it's a bit more of a curve. But yeah, you just need to make sure that it shows that it's a decrease in yield as temperature increases. A preservative added to some fizzy drinks is made by reacting sorbic acid with potassium hydroxide. In an experiment, 7 grams of sorbic acid, C6H8O2, is reacted with 250 cubic centimeters of potassium hydroxide solution, concentration 0.5 moles per liter. Show by calculation that the sorbic acid is a limiting reactant. Okay, so what we're going to do here is, because this is a 1-to-1 molar ratio, I'm just going to calculate the number of moles of the sorbic acid and the number of moles of potassium hydroxide and see which one is bigger. So for sorbic acid, it says that we've got 7 grams of the stuff, and it's got 112 4A mass. So that means number of moles will be 7 divided by 102. So 7 divided by 102, that will be this really small number. And then we'll do the same, but we use the volume, the concentration volume thing, equation. And then we're going to have the concentration is 0.5 moles per liter. But remember, volume is in liters, so it's not 250. It's going to be 0.25. And then we're going to go and do that, which will be 0.125. But I'll just do it in a calculator anyway, just in case I flip up completely. Look at that. Always stay winning. And we can clearly see that there's more moles of the potassium hydroxide solution. So therefore, just really spell it out here, is less moles of sorbic acid than moles of potassium hydroxide. So sorbic acid is the limiting reactant. Right, move on to C. Ammonium ferric citrate can give some drinks a characteristic orange colour. A typical drink contains 0.002 percentage of ammonium ferric citrate. A 1% solution contains 1 gram made up to 100 cubic centimeters of solution. Calculate the number of moles of ammonium ferric citrate required to make 330 cubic centimeters of a fitted drink. Okay, so the way I'm going to figure this out is if 1% solution contains 1 gram, that means a 0.002% solution would mean 0.002 grams in 100 cubic centimeters. So we need to calculate how many moles that is. And the moles would be, it'd be an extremely small number. We're talking on the, like, it's already small enough, but you just have to make it even smaller. So 0.002 divided by 261.8. That gives you that horrific thing, which your calculator won't even represent as a normal number. So we're on thin ice here. So it'll be 707.64 times 10 to the minus 6 moles per 100 cubic centimeters. So that means N equals CV. We know it's 7.64 times 10 to the minus 6. I'm writing that way too small. Equals, you don't know what a concentration is, but we know the volume is 0.1. So we're going to divide this by 0.1. Which should give us the same number, but so the concentration will equal 7.64 times 10 to the negative 5 moles per liter. So now, after all that, we can go down and say N equals CV. Concentration is 7.64 times 10 to the negative 5. The volume of 0.33. So how many moles is that? Just double checking everything's alright. That would be 2.52 times 10 to the minus 5 moles. Yeah, so extremely little ammonium ferric citrate in the solution. Ginger root is used as a flavouring for some fizzy drinks. Ginger oil is an essential oil obtained from ginger root. Zingiberine is one of the main components in this essential oil. State one property of an essential oil, and that would be this essential oils, remember, are very volatile. There's a few other properties that you could actually talk about. You can also say strong aroma. But you could also say they're not water soluble. So yeah, those are the base kind of properties, three properties. So you can choose any of one of them. So I'm going to pick here. I'm just going to say volatile. That you can choose either one of these. Because yeah, volatile is just wise, one word. But anyway, zingiberine is formed from isoprene units. State the type of compound formed when isoprene units join together. That would be everyone's favourite, terpene. Isoprene is also called 2-methyl-1,3-butadiene. Draw a structural formula for isoprene. So yeah, what we're going to have here is we're going to have a double bonded carbon, and then it's going to link to another double bonded carbon. You see we've got the 1,3 for the diene, and then we have a 2 on the methyl group on the second carbon atom. So that means we can do that, and then we just need to populate the rest with hydrogen atoms. So this carbon here has 2 slots remaining, so we have 2 hydrogen. This one has all 4 taken up. This one has 1, so we can have another one, and then we can have 2 more hydrogen atoms here, and that should be our structural formula for isoprene. State number of isoprene units in the zingiberine molecule. So what we're going to do here is we're going to actually go and count up all the carbon. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And since each isoprene unit is 5, 15 divided by 5 is 3. Gingerol is another compound found in ginger root. Gingerol can form from the compound chagarol as shown. Name product X that is produced. So whenever it says name product X, it's either carbon dioxide or water, to be honest. So you could just put one of them, but it's best to probably actually go and figure out what it is, obviously. But you can clearly see here that we are removing a 2 hydrogen atoms, because there should be one there, there should be one there, and there should be an oxygen there from the base one, base molecule. And do you know what that means? 2 hydrogens and an oxygen. That's H2O, otherwise known as water. Name 2 functional groups present in gingerol and chagarol that are not present in zingiberine. We can see here that we have a carbonyl group, and we also have a hydroxyl group. But we'll just check if any of those are present in our zingiberine. There aren't, so let's go and just write them down. So that'll be carbonyl and hydroxyl. Second, using your knowledge of chemistry question. For a particular set of reaction conditions, the actual yield is the quantity of desired products made in reaction. Some examples of reactions which the desired products are shown. Using knowledge of chemistry, describe the actual yield in reactions could be determined. Your answer should be schooled in experimental procedures that can be used to determine the quantity of products made in reactions. The examples shown from the table. Okay. So basically, this is what we want here is we want to get a system that could allow us to measure how much stuff is produced by each of these reactions, and it gives us 3, which is a nice for 3 marks. So let's go one by one, and I'm going to go with this first reaction at the top. So let's write out the whole equation just to be absolutely sure. Plus, NCFO. We're going to have to go into the other line, finish this off. I always seem to write my A's as Q's for some reason. And there we go. So our desired product here is this solid barium sulfate, I believe. So what I'm going to do there is I'm just going to see if I can remember where I put my there we go, there's our relationship sheet. So let's go look at barium sulfate in our solubility table, because that means we know if we need to evaporate it or we need to filtrate it. I'll have a look at what that's sodium nitrate, and see what that is as well. So, oops, barium sulfate, that is insoluble. So yeah, that's why it's a solid, so it would be a precipitate. What is sodium nitrate? That is very, very soluble. So that means we're going to have to evaporate that. We're going to have to get rid of that. Well, we can just filtrate it. So we can say, I'm going to start writing it out. To measure the quantity of barium sulfate produced by the reaction, filter the product through some filter paper, hang on, we need to before we do that, we need to measure the weight of clean filter paper. Then filter the products through the same filter paper. Where we want to then dry the filter paper in an oven to remove I need to wash it out first, don't we? So we need to out the filter paper to remove any soluble filter paper with water, soluble impurities, then dry it out in an oven. Measure the filter paper new weight and compare and then find the difference between that and its original weight. The difference is in weights is the mass of barium sulfate produced. Yep, there we go. The yield could then be calculated by measuring the amount of reactants used, and then calculating what theoretical mass of barium sulfate could be produced using the molar ratios in the reaction equation. Right, that's a pretty bad answer, so we'll go and add, so I think that's a fairly okay answer, I mean, for the first equation, and I'm going to do the for the other ones. So I think I'll write the formulas later. I'll just keep going. So for this next reaction, we have that's methanol. I'm reacting it with what looks to be ethanoic acid, otherwise known as vinegar, and we're going to get is that a or is that, yeah, that's an ester. So we're going to produce an ester and water, and we want Oh, we want the ester, which it would be methyl ethanoate, if I'm thinking correctly, as our desired product. The quantity of ethyl ethanoate. Oh no, it's propanoate, wouldn't it? It could be measured by. So remember that you're not actually ever going to get a perfect amount produced, because they are always going to be in equilibrium with water. All right, I've done my research. The quantity of ethyl could be measured by condensing, by evaporating the products of the reaction, and then condensing the ester, allowing us to collect it. And I'm going to draw a diagram below. Collect it, and then measuring its volume. Measuring its mass using a balance. I was going to use like a measuring cylinder, and I realised how inaccurate that is. So balance zeroed to the test tube. Right, and then the diagram I'm going to use is going to be, oh, they actually don't give us any room at all, do they? Okay, well, I'm going to take out these. But essentially what the diagram would be using would be a really bad condenser. So you'd have your reactants in a, like a sort of a water bath here. So you'd have, what would be, it would be methanol, and you would have a propanoic acid, and then we're going to have heat at the bottom, and then we're going to have cold water here. And then the idea is that whether we have another test tube below it, so this will act as a really bad condenser, and then the products will drip, will get stoked in and then drip down, and then we can collect it. So yeah, I could actually go and scroll to the, oh, they don't even provide me with extra paper. Well, that's all you're going to get, but you can talk about the previous answer as well. So what I would do here is that it's a gas, so you can go, so yeah, quickly you can basically say, okay, well, I'm going to use a conical flask with a hydrochloric acid here. And then we're going to have chips magnesium. And then we're going to have a pipe that leads to a gas syringe where you can measure the volume of your reactants, or your products, I mean, your desired products, because this solution stuff will stay there, it won't go up. And then remember to have a stopper. So yeah, I'm going to run out of room, but you could go pretty, you can talk a lot about this. Moving on to 10. A refrigerant is a chemical used in cooling processes. Some refrigerant compounds can damage the ozone layer. The ozone depletion potential, ODP, of a refrigerant compound is the relative amount of damage that can cause to the ozone layer. The higher the number, the greater the damage. See here, we've got on the table, describe a relationship between the formula of refrigerant compounds 3, 4, and 5 and their ODP. So we only want to look at 305 and see 3, 4, 5 and see if we can find any things. So for all, we can't mention anything about carbon because they all have the same amount of carbon. You can see that increasing the amount of fluorine actually decreases the ozone depletion of the potential, and increasing the amount of chlorine increases it. So let's go and say increasing the number of I need to put space there, don't I? Oh, sorry, I pressed F. I pressed F 11 by accident, guys. Horrific. Of chlorine atoms gives a higher ODP. Identify which pair of compounds could be used to show the effect of replacing chlorine atoms with bromine atoms in refrigerated compounds. So it looks like I think 1 and 5 would do it, because we both have the C2F F4, but then we just replace the last 2 atoms with bromine or chlorine, so it'll be 1 and 5. The refrigerants carbon dioxide and ammonia have ODP values of 0, so that's why this is the case. They do not destroy the ozone layer. Oh no, because they don't contain halogen atoms. They do not contain halogen atoms, so do not damage the ozone layer. The compounds difluoromethane is also used as a refrigerant. Is made by reacting fluorine gas with fluoromethane in a free radical chain reaction. State what is meant by a free radical, and that is a molecule, a particle, which could be an atom, it could be an electron with unpaired electrons. You could also say species if you want to be weird, but the first step in the reaction involves splitting a fluorine molecule to produce 2 fluorine radicals. State the name given to the step. This would be initiation. This is when the whole thing starts. What are the possible propagation step in this reaction? So just remember we're reacting with this, so we just need to have a free radical react with this and see what happens. With fluoromethane, sorry, so it'll be CH3. So I'll go and see what happens. So I have our radical, and we're going to react it with CH3F. What does it get produced? Well, it will turn this into a CH2, because fluorine would really want to steal, really wants to get a proton, because it's got an unpaired electron, so it's really wanting what is a proton? I mean a hydrogen ion. So it's going to steal this hydrogen ion from this molecule, and it's going to steal it so fast that this molecule is actually going to become a free radical, as fluorine makes off like a band and produces a stable molecule of HF, which is written as FH for some reason. And there we go. Household fridges use coolants made from refrigerated compounds. Common coolant is made from 50% difluoromethane and 50% pentafluoroethane. A typical fridge contains 0.05 kilograms of coolant. Calculate the number of moles of pentafluoroethane required to make this mass of coolant. Okay, so basically, since they're 50% either way, we're going to go and divide this by 2. So that means we need 0.025 moles, 0.025 kilograms of pentafluoroethane, which is what we actually want to calculate. And so we'll convert this into grams. So that'll be 25 grams. So then we go N equals M over FM. M is 25. Fluorocarbon, that would not fluorocarbon, the formula mass would be 120. So number of moles would be 25 over 120, and that would be this number here, 0.208 moles. On to our final questions. 11. Spinach is a leafy green vegetable. Whoa, crazy! Didn't know that. Fertilizers containing copper-2 FNO8 are used to supply spinach with copper ions. Copper-2 FNO8 can be made by reacting copper-2 carbonate with ethanoic acid, namely other products of this reaction. So copper-2 FNO8 can be made by reacting copper-2 carbonate with ethanoic acid. So remember when I say that if you don't know what the products are, just say water and its other products, so it would be water and carbon dioxide. But why is that? And that's because you're reacting a salt with an acid, and that would be a reacting. This is actually a hidden neutralization reaction. So this is actually here. This is a salt, right? And then this is copper carbonate is actually a base, an alkali. And then ethanoic acid is of course an acid. So this is a neutralization that produces salt, water, and carbon dioxide. Write the ionic formula of copper to FNO8. So you could actually do a full structural formula, but let's just do let's do a proper formula. So we're gonna have copper 2 F108. That means that we need to go and draw an F108 first. Oops. So remember F108, that's 2. Because this is a salt, instead of using OH, it's actually going to be OH negative. It's just going to be O negative, and we're going to have Cu 2 plus. But notice anything weird. This is not balanced. We need to have a neutral molecule, which means we're going to have another one over here that's also bonded to this copper atom. And there we go. And it's all fine and dandy. Spinach is a source of oxalic acid. A standard solution of oxalic acid can be used to determine the accurate concentration of a sodium hydroxide solution. Given an accurately known mass of acylic acid, describe fully how 250 cubic centimeters of a standard solution of acylic acid could be prepared. So what would you do? Well, you're going to go and this is a boilerplate thing. You can pretty much do anything. You can say you dissolve oxalic acid or whatever you're going to dissolve in a small amount of water, in some water in a beaker. Then transfer the water to your volumetric flask. Rinse the beaker and add the rinsings to the volumetric flask. The flask, not flash. And then add water until the bottom of the meniscus touches the 250 cubic centimeter graduation line. The concentration of a sodium hydroxide can be determined with type of titration with acylic acid. An accurate volume of sodium hydroxide solution is measured into conical flask using pipette. you draw a diagram of a pipette suitable for measuring an accurate volume. Okay, so what we need here is a basically we just need to draw a pipette with a scale on it. So you all know what a pipette looks like, hopefully. But you can either use a volumetric or graduated pipette. So I'm going to do a graduated pipette because it's the one I'm more familiar with. But it's essentially just a big tube with it's like a big pencil really, with a top, and eventually you have a series of valves up here that allow you to put in liquids. But we'll just draw the glass thing, and then all we need to do now is make sure we have a scale on it. And there we go. The indicator used in this titration is phenolphthalein. Phenolphthalein is colourless in acidic and neutral solutions, but it's pink in alkaline solutions. State the colour change that will be observed at the end point in this reaction. Well, this is a sodium hydroxide solution, and then we're adding oxalic acid to it, so it's going to be alkali. So it's going to start pink, but then at the end product, when we turn it to a neutral, it's going to be colourless. The titration was repeated until the results obtained that were within 0.2 cubic centimeters of each other. State the term used to describe tighter volumes within 0.2 cubic centimeters of each other. That's going to be within concordant. And then finally, very last question. The equation for the reaction of acidic acid and sodium hydroxide is shown. The concentration of sodium hydroxide solution is determined by titrating 25 cubic centimeter samples with 0.126 moles per liter acidic acid solution. The average volume of acidic acid solution required in the titration was 26.75 cubic centimeters. Calculate the concentration in moles per liter of sodium hydroxide. All right, let's get cracking on this then. We want to figure out the volume of this. What concentration of this, and then we know that we can titrate the average volume of the oxalic acid required to fully react with this. So the average volume of this is 26.75, and we know it is this concentration. So let's calculate the number of moles of acidic acid we needed, and that's going to be 0.126, and then times by the average volume, which remember we're doing it in litres, so it's actually going to be 0.26575, and then that's going to give us a massively small number. That's going to, it's going to be quite small. Keep it in your calculator, as I said before. And then all we need to do now is go and say, well, one other thing we need to do, remember, is say this is a 1:2 molar ratio. So that means that one of these can dissolve 2, so we can actually times this by 2, because then that'll give us the number of moles of sodium hydroxide. So that'll be 0.006476741. And then we can just plug it into our equation again to figure out the concentration. So we know that it's this many moles. Equals, we don't know what the concentration is, but we do know it was 25 cubic centimeters of volume, so it'll be 0.025. And then we're going to go and divide this by that. So divide 0.025. So that means the concentration must equal 0.27 moles per liter. And there we go. That is the entirety of 2022, paper 2, higher, whatever. I completely lost my brain over the past 2 hours. So yeah, good luck in your exam. It should be, hopefully I'll actually upload this today. I have a very bad track record with that, however, but I'll really try and pull in tonight. So good luck in your exam on Thursday, and yeah, mash out.